SpaceX has spent more than $15 billion developing the Starship rocket system, a number pulled directly from the company's own confidential IPO filing reviewed by Reuters in May 2026. That figure dwarfs the roughly $400 million SpaceX spent building the Falcon 9, which remains the most flown rocket in history. At the center of that $15 billion commitment sits a single piece of hardware, the Raptor engine. Raptor runs on what engineers call a full-flow staged combustion cycle. Most rocket engines bleed off some propellant to spin the turbopumps, venting that exhaust overboard and wasting a fraction of the fuel. Full-flow staged combustion sends 100% of both the fuel and the oxidizer through preburners before either stream reaches the main combustion chamber. The efficiency gain is real. Getting there is where things get brutal. Two separate preburners have to run simultaneously, one oxygen-rich and one fuel-rich, and both streams must convert entirely to gas before entering the main chamber. The oxygen-rich side is where history kept stopping. Hot gaseous oxygen under extreme pressure doesn't flow through metal, it eats through it, and no commercially available alloy could survive those conditions. Before Raptor, exactly two full-flow staged combustion designs in all of aerospace history had reached a test stand. The Soviet RD-270 in the 1960s never solved its combustion instability problems. The Aerojet Rocketdyne integrated powerhead demonstrator in the mid-2000s proved out the powerhead only and never flew. Two attempts across 6 decades, and neither made it to orbit. September 2016 changed that when SpaceX's subscale Raptor demonstrator fired at McGregor, Texas, becoming the first full-flow Methalox engine in history to reach a test stand. Getting the oxygen-rich preburner to survive at all required SpaceX to invent metal it couldn't purchase, developing a proprietary superalloy in-house, first called SX300, later refined into SX500, capable of containing hot oxygen gas at up to 12,000 pounds per square inch. Raptor 2, entering production in late 2021, pushed chamber pressure to 300 bar, breaking the previous world record held by Russia's RD-180 at 267 bar. Musk told reporters in February 2022, "This engine has been mind-bogglingly difficult, but it is essential to making Starship work." Raptor 3 then hit 350 bar in testing in May 2023, and Musk's reaction on X was unguarded. "To be frank, we did not expect the engine to survive a full-duration run at that pressure. Raptor chamber wall might have the highest heat flux of anything ever made." Reaching those numbers required relentless subtraction as much as engineering addition. Raptor 1 earned the nickname Christmas Tree because it was so covered in external pipes, wires, and sensors that it barely looked like a single object. Raptor 2 stripped most of that away, dropping engine mass from 2080 kilograms down to 1630 while pushing thrust from 185 to 230 tons force. Raptor 3 internalized virtually all remaining secondary flow paths and added regenerative cooling to exposed components, eliminating the external heat shields entirely and pulling roughly 6 tons of fire suppression hardware off the super heavy booster in the process. When the first Raptor 3 photo appeared in August 2024, United Launch Alliance CEO Tory Bruno publicly accused SpaceX of showing a partially assembled engine. It looked too clean. It was, in fact, SpaceX's most complete engine to date.
Raptor's original concept called for hydrogen as the fuel. In November 2012, Musk announced publicly that methane would replace it, with no orbital rocket ever having used liquid methane before. 3 compounding problems drove that decision. The first is Mars. Every kilogram of return propellant carried from Earth to Mars has to be launched off Earth first, and the mass economics of a round-trip mission at any real scale simply don't close if you're hauling all that fuel from home. Methane dissolves the problem because Mars can make it. The Martian atmosphere is roughly 95% carbon dioxide. Confirmed water ice sits in the subsurface, and a well-established chemical process called the Sabatier reaction combines those inputs to produce methane and water. NASA confirmed that in-situ methane, oxygen, and water production on Mars is viable, and using locally produced propellant cuts required Earth-launched mass by 5 to 10 times compared to carrying return fuel. That same Sabatier reaction runs continuously on the International Space Station for carbon dioxide scrubbing, so the chemistry isn't speculative. The second problem is reusability. SpaceX's Merlin engine burns RP-1, a refined kerosene, and kerosene combustion leaves carbon deposits that accumulate in cooling channels and foul turbine surfaces over repeated firings. Methane burns clean, leaving almost no soot, and not difference is the mechanical foundation of Starship's entire reuse model. The third problem is hydrogen. Better efficiency than methane, but liquid hydrogen boils at -253 degrees Celsius, demands enormous insulated tanks, and can't be produced on Mars through the Sabatier process as a usable end product. Methane stores at -161 degrees Celsius, packs more energy per volume than hydrogen or kerosene, and costs less per unit of impulse than either hydrogen or kerosene. Engineers call it the golden mean. As of 2023, no orbital-class methane engine had ever reached orbit. SpaceX committed billions to a propellant with zero flight heritage at that scale. Blue Origin, pursuing similar goals with its BE-4 engine, also chose methane, but picked a simpler combustion cycle. SpaceX chose full-flow staged combustion precisely because extracting maximum efficiency from methane required the most complete combustion cycle available, and those two decisions were locked together from the start. April 2021 brought outside validation when NASA awarded SpaceX a $2.89 billion contract for the Artemis 3 lunar lander, built around the methane-burning Starship, selecting it over Blue Origin's national team bid because SpaceX's price was, in NASA's own evaluation, the lowest among the offers by a wide margin.
Early Raptor 1 engines cost approximately $2 million each. Each complete Starship stock carries 39 of them, 33 in the Super Heavy booster and 6 in the upper stage. At $2 million per engine, propulsion alone on a single vehicle runs $78 million before a structural panel gets welded. SpaceX's target for a mature Starship launch is $10 million total. Closing that gap is the entire industrial challenge of the program. Over the Thanksgiving weekend of 2021, Musk sent an internal email describing the Raptor production situation as a crisis that was much worse than it had seemed a few weeks ago, spending the holiday personally on the factory floor and warning the company we will need all hands on deck to recover from what is, quite frankly, a disaster. Bankruptcy wasn't rhetorical. Musk described it as a genuine risk. Roughly 1 year later, SpaceX was building Raptors at approximately 1 engine per day, announcing its 200th upgraded engine on November 4, 2022. That turnaround required redesigning what the engine was allowed to be. Raptor 2 removed flanges, stripped development sensors, and consolidated valves, cutting 450 kilograms of hardware per engine, which, across 33 booster engines, came to nearly 15 tons removed from the vehicle. Raptor 3 then eliminated the booster heat shields entirely by internalizing all remaining flow paths, pulling another 6 tons of fire suppression hardware off the stock, while simultaneously raising thrust from 230 to 280 tons force, and trimming engine mass to 1,525 kilograms. More thrust, less weight, fewer parts, simultaneously. Musk's guiding principle across all of it, the best part is no part. SpaceX's own IPO filing puts total Starship investment at over $15 billion. NASA's Space Launch System cost roughly $24 billion to develop and burns about $2 billion per launch, with the rocket discarded each time. SpaceX's target is $10 million per Starship launch, a potential 200-fold reduction, and that number only works if 39 engines per stack can each be built for $250,000 and reflown with minimal servicing. By April 2026, SpaceX had produced more than 600 Raptor engines total, with over 40,000 seconds of accumulated runtime on the Raptor 3 generation alone.